Welcome to another exercise for the workbook Statistics, this time focusing on measures of contingency, or rather on measures of association for normally scaled variables. Our exercise here: you work for a travel agent and want to know whether a relation between your customer's gender and their general satisfaction with your services exists. In this context, you collect the following information, giving us this table here. And our task now: calculate a suitable measure of association to quantify the strength of the relation between the two variables. I'm directly saying, well, we could use the Yule coefficient here, but I would rather go with something based on chi-squared because the results are usually much better to be interpreted. And Yule also only works because it's a 2 times 2 contingency table. So let's go with chi-squared first and then decide what else to use. First step to actually get to chi-squared are the marginal frequencies. So I'm going to add one column, one row here. I'm going to add the totals for each column and each row in them. So that's the totals for this column, this row, that row. Then I'm going to add those two or those two up, giving me the overall number of observations, which is here 120. Using these marginal frequencies, I can then calculate the so-called expected frequencies. Those frequencies I can expect if the distribution of values of participants, people, guests, and so forth here would be evenly distributed following only those marginal frequencies. For this, I'm going to use the same table as before, but I'm going to replace the values in here. I'm going to replace them with this formula. This might look strange, but this simply means I'm going to take the row sum, the column sum, those two. I'm going to multiply them, that's the upper part here. I'm going to divide this by the overall number of observations. So here, 54, 66, 120. I'm going to do the same thing for every of those values. So here, 54 by 120. 66 by 120. 66, 54 by 120. So those are the expected frequencies. And then chi-squared simply goes on and compares actual values and expected frequencies and takes a look whether the actual values are closer to the expected frequencies, which would mean, well, we follow no real structure, or if they are relatively far off from these expected even distributions, whether we have a significantly established structure. So if there are large deviations, large chi-squared, we have a strong relation. Small deviations, small chi-squared, weak relation. Well, how to calculate this? Here I'm just going to copy the original values on the left, the expected values, frequencies on the right for all 4 entries, and then I'm going to use this formula. This simply means for each entry, calculate this part. And this is nothing else than expected value, so for example 29.7, minus actual value, minus 21, in brackets, squared, divided by expected frequency, divided by 29.7. I'm going to calculate this for each of those 4 entries. I could do this in the table. This would help, for example, if you're doing this in an exam, would help you get a better overview. What have you already done? And would maybe avoid some confusion. Did I already cover all of the different values I need? Here I'm just going to note this. I have 4 entries, so I need 4 different terms. Each same structure, expected value, actual value, expected value. I'm going to put this in a calculator, giving me an end result of 10.2969. That's my chi-squared. Chi-squared itself doesn't actually tell me a lot because this is somewhere between 0 and infinity. So I cannot really interpret this, and that's why I need an additional statistic based on this, usually a normalized statistic. Here I could use, for example, Kramers V, phi, or as I'm going to do here, the contingency coefficient. So let's turn to the next slide and talk about how to get to the contingency coefficient starting from this chi-squared statistic. So I'm going to copy this chi-squared statistic from before. And the contingency coefficient simply is this formula. So I need chi-squared, which I have, and I need the number of observations. So the contingency coefficient also takes care whether I have a lot of observations or very few, because more observations means more potential for deviations. Well, I'm going to insert both values, giving me a result of 0.2811, which, however, while it's smaller than 1, is not a normalized indicator because the upper bound is not necessarily 1. So I need to correct this first. The correction, I'm going to use the parameter m for this. That's just the minimum of number of columns and rows. Here I have a 2 times 2 table. So row number and column number are both 2. So my m is 2. Therefore, my correction factor is 2 divided by 2 minus 1. So 2 divided by 1 and the square root thereof. So it's basically contingency coefficient k times square root of 2. I'm going to calculate this as I get as a result 0.3976. And that's a value I can now interpret using the same thresholds I know for other measures of association. This is somewhere between 0.3 and 0.5. Therefore, it's a medium strong relation. We had the threshold 0.1, 0.3, 0.5. Below 0.1, there's no relation. 0.1 to 0.3, weak. And then, well, 0.3 to 0.5, medium, and larger than 0.5, a strong relation. It's a medium relation. We cannot say anything about the direction because, well, it's nominal data. Nominal data does not have any kind of orientation, so we're stuck only with an information about the strength of the relation. And well, that's then everything there is to this exercise, which I hope you enjoyed. I say goodbye and see you next time.